Hi, my name is Sam Somerville, and this is a supplemental video for ME 557, Design for Manufacturing. And in this video, I'm going to be talking about the design for manufacturing practices for investment castings. When you see components such as turbine blades with complex internal air passages, jewelry with minuscule and intricate designs, or endoscopic medical tools which require smooth surface finishes, you're looking at parts that were likely investment cast. Investment casting is a manufacturing method which has been around since the Bronze Age for jewelry, but is now used in high precision industries, primarily aerospace, medical, and energy, as a powerful primary forming method that comes with exceptionally smooth surface finishes and tolerances. In this video, I'll be talking about the investment casting process and the applicable DFM guidelines. My goal is to present the following content in a way that mirrors how we've been taught to consider designing for other manufacturing processes in class. First, I'll cover the steps involved in the investment casting process and draw some comparisons to the other methods that we've already learned about in ME 557 to help provide context behind the benefits and constraints of this casting method. Then, we will get into the DFM topics by discussing the physical phenomena which inform the standard design for manufacturing guidelines, as well as a brief overview of the steps required for estimating the time required for investment casting. As a side note, this video will not be going into the cost estimation model for this process. As I'll show later on, investment casting is a long and extensive process, meaning that the cost estimation model would make for its own 20-minute video. With that being said, let's dive straight into how investment casting is performed. The first three steps are really what matters the most, so we'll cover those in a little bit more detail. The first step to the investment casting process is creating the wax mold pattern. The initial mold is typically created by machining the desired pattern directly into a metal mold. Different metals are better suited for different types of wax, and the wax you plan to inject will determine the initial mold requirements. In general, the liquid waxes are less abrasive and are injected at high temperatures and low pressure, making aluminum a common choice for the metal mold. Alternatively, solid waxes and plastics are injected at lower temperatures but are more abrasive and require higher injection pressures, making tool steel a better option. It's also important to note that wax molds last indefinitely, but plastic molds should be replaced about every 1 million cycles. That being said, the most common waxes used for investment casting are paraffin or microcrystalline waxes. Using metal molds and injecting wax can be avoided altogether by just 3D printing your desired part directly in a castable resin. But this method sacrifices tolerance control in place of saving cost and time. But this is still useful for the initial testing of an investment casting process or output of a mold geometry when cast in final metal while the real production mold and process is being designed. Moving on to step two, once a collection of individual wax molds are created, they are joined to a central wax tree. These trees are what make investment casting so efficient for small parts as multiple parts can be created from a single pouring operation. Wax trees are formed by the hands of very experienced practitioners or by 6-axis robots. The trees can comprise combinations of different waxes and plastics that melt at different temperatures and provide different surface finishes. Once the wax tree is created, it's ready for its ceramic shell. In this step, the shell is built around the wax tree pattern. This will be the actual mold which will receive the molten metal later in the procedure. The wax tree alternates between being dipped in a ceramic slurry and being dusted with stucco particles while ensuring sufficient drying between each layer. The initial ceramic layer must contain fine grained particles, as this will be the direct surface that will dictate the surface finish of the final part. Subsequent layers of the slurry can be coarser and mixed with binders to strengthen the mold. The stucco powder that is applied between the ceramic layers is necessary to prevent cracking, build thickness, and prevent layer separation. Anywhere between 6 to 10 layers of combined slurry and stucco will be applied to ensure the shell is thick enough. However, you don't want your shell to be too thick, otherwise, you run the risk of not being able to remove it to retrieve the finished part later. After allowing the ceramic shell to dry, we will now have a hardened shell with the wax parts inside. For step 4, we want to remove the wax from the shell to prep it for metal casting. This step either uses a steam autoclave or a flash furnace. The idea is to rapidly heat the wax to cause it to melt before it's able to expand and crack the mold. Using an autoclave typically allows wax to be retrieved and reused, whereas flash removal may burn the wax in the process, making it unusable afterward. Step 5 is firing the mold. The ceramic shell is simply placed in a kiln to cure, similar to how you would with normal pottery. This step achieves two things. First, it allows the mold to harden further and cure in preparation for the molten metal. The second goal is to remove any excess moisture embedded in the shell or any residual slurry material. When transitioning to step 6, it's preferred to keep the mold in its heated state from firing. Some manufacturers opt to let the shell cool for inspection prior to metal pouring, but this would require a separate heating cycle and further increase the time to manufacture. An alternate method to inspect while avoiding this is to make a separate sample of the ceramic shell mixture used on each wax tree specimen to inspect for deficiencies in the meantime. One way or another, the desired metal is then poured into a fully prepped mold. There are ways to manipulate and improve the crystal direction and formation at this step, but I won't get into that level of detail here. Once the metal has sufficiently cooled inside the shell, the parts are ready to be extracted. First, the ceramic shell needs to be removed. Most of the shell can be removed by shaking the tree with a pneumatic hammer, and remaining chunks are shot blasted. If preformed ceramic cores are used in this design, then they are dissolved by dipping the finished tree into a caustic bath at this step. And finally, you are left with a metal tree of components. All that needs to be done now is remove the individual parts and finish them as desired. So, from these steps, you can tell that this is a very time consuming process, requiring more steps and longer lead times than sand and die casting. This problem is exacerbated when you consider that your casting process will need to be validated using hundreds of trials without seeing a single defect before it can be implemented for production. Prayed for this is that when you do create the process correctly, you can achieve a very smooth finish and tight tolerances straight out of the mold when compared to other primary forming methods. This can often remove the need for extensive post processing or machining, meaning you're also going to be saving costs by not producing as much scrap metal. These savings add up when using expensive materials. And speaking of materials, this method allows for you to cast a wide range of materials due to the high temperature capability and stable molding environments of the ceramic when compared to die and sand casting, which are respectively limited by temperature and a risk of unwanted chemical reactions from the introduction of metal to the sand or silica. Finally, above all else, Boothroyd and Dewhurst claim that investment casting provides the most freedom of design than any other metal forming operation. This method enables you to achieve complex geometries that are tricky or even impossible to produce using any other forming method. This is largely thanks to the robustness of the wax replica method and being able to implement soluble cores into the wax tree, which are easily removed during the wax draining process. Now, if you look at our list we have going here, there isn't just one con for choosing this method. The next con goes hand in hand with the long manufacturing time. That is, this process is not optimal for very large batch sizes. In this metric, die casting is still the go to method. You'll also have to consider that you're essentially paying to perform two manufacturing processes in one. Assuming this is a large scale operation, injection molding will be the go to process to create the wax replicas. This makes the tooling cost for this method high compared to other casting methods. We'll get a better idea of how extensive this gets when we get into the time estimation model. And the last primary constraint are the size and weight of your resulting metal parts. Large ceramic shells are hard to handle without cracking them, and while this process can support components ranging between half to 100 kilograms, it's typically best advised to use this process for parts less than 5 kilograms for your typical ceramic and stucco shell construction. The physical phenomena observed for this kind of casting are very similar to sand and die casting. These phenomena are nothing new, so I'm not going to spend too much time discussing these in detail here. But what we learned for sand and die casting is that these phenomena drive design decisions for both the part and mold design. Investment casting differs from this outline by introducing the need to design for the wax mold alongside the ceramic mold and the finished part. Luckily, because the wax mold step is an injection molding process, we can refer to the design best practices for injection molding to assess the guidelines for stage 1 shown here. And we can refer to the casting guidelines to assess stages 2 and 3. So, keeping these relations in mind, let's see how the guidelines for investment casting translates and deviates across these three facets of design. Overall, the wax mold design doesn't deviate much from the general injection molding guidelines. There's also the added benefit that injection molding and casting share similar design guidelines, meaning we won't have to jump through as many hoops while considering how to design the process for the wax replica versus the final metal part. Starting with the wax mold guidelines, there's one unique consideration to translate from the injection molding rules, which won't apply to the other two stages. That is, locating the mold parting line and positioning the part sensibly along said parting line. Other than that, the other basic guidelines still apply, including incorporation of drafts and uniform walls. This facet deviates from standalone injection molding largely because the part will not be final, and therefore will not need to have the same structural or functional requirements as the final part would need. The part, at this stage, is purely a replica, so choosing the cheapest material that can attain the desired surface finish and geometry in the final part is really the key here. For stage 2, we look at the casting guidelines. Designing with gates is still applicable, although the reason is slightly different. A runner will always run downward axially through the tree mold, and the number of gates required for one part in the tree will need to be replicated throughout the entire pattern. This impacts the pattern density that fits into the tree mold. Too many individual patterns may increase turbulence or risk incomplete filling in some areas. Alternatively, too few patterns will result in wasted shell volume that could have been used to make more parts per operation. Rules that can transfer over are the need to work in runners, sprues, and risers, since these are still needed with ceramic tree molds. However, these mold features are less intrusive to the overall design because the passages are smaller and smoother compared to sand castings. Additionally, parting lines and screens are no longer cause for concern since this process doesn't use a clamped mold design or sand. Finally, as mentioned earlier in the video, investment cast parts are less reliant on preformed core usage, as the initial wax patterns can include self-coring geometry in many cases, so that can be added to the deviations list as well. The third facet of investment castings is the finished part itself. Again, we can draw from the information we have on casting guidelines that apply to other methods. The fact that I'm looking at the finished part last doesn't necessarily imply that these guidelines should be considered after the molds have been designed. In fact, the final part should be assessed to make sure it's suitable for investment casting in the first place. The most important rule here is to make sure the intended production volume is suitable for the process. In this case, between 10 to 10,000 parts are the most suitable. Otherwise, just make sure that the material and design features accommodate the process. Although, choosing investment casting will provide more allowance with the material selection and geometries. Now, you may be wondering when I say just make sure that the material and design features accommodate the process, what kind of features does this encompass? The short answer is a lot. But I realize that it's not very helpful to someone actually looking to implement these design practices into their parts. I personally find that it helps to have a reference of actionable design practices that I could implement into my own part geometry if I was designing something from scratch with this method in mind. So, to cap off the design guidelines section of this video, I provided this table with some common design practices to follow and the phenomena or constraints that necessitate these design decisions. I won't go through each one of these lines in detail, as many of these concepts are provided in ME 557 course readings, such as chapters 8, 10, 12, and 13 of Product Design for Manufacture and Assembly by Boothroyd and Dewhurst. But feel free to pause the video to refer to this list. In general, I found that material selection can add additional variability in the limits that you can get away with for your part when applying these DFM principles. As we learn in class, it would be advisable to select the material early on, depending on your thermomechanical property and dimension constraints. Let's go through a quick example. Some examples of constraints you might see could be that your material must be capable of forming a wall thickness of 60 thousandths. Let's say that your part needs to fit within a desired design envelope of a broader assembly. We'll say that the part needs to be capable of withstanding a temperature of 500 degrees Fahrenheit while also minimizing the weight of the part. Now, you can take this kind of quantitative info to create design variables to input into a DFM tool, such as Granta EDUPack. Then, using this tool, you can determine a suitable material for your process or for your application. Once your material is selected, then you can look up the specific casting guidelines to ensure that the rest of your part will conform to the material's casting capabilities. So now that we've gone through the meat of design for manufacturing for this process, I wanted to end things off by providing a brief overview of the models that are used to estimate notable cycle times along with different stages of the investment casting process, while also providing some resources for diving deeper into these topics. Again, these outlines are referenced from Boothroyd and Dewhurst. If you own a copy of this textbook and take a look at the chapter contents for investment casting, the cost and time estimation makes up for over half of the entire chapter. So, this would probably take an entirely separate video to cover these in any sort of meaningful detail. So, instead, I've created some flowcharts to help fellow students navigate through the process of estimating the time for manufacturing. So, this flowchart goes through the production cycle time as outlined by Boothroyd and Dewhurst. It can loosely be broken up into four sections: the injection cycle time, max mold manufacturing time, pattern cluster time, and the post processing time. The injection cycle comprises three main steps, which are the fill, reset, and cooling time. The injection cycle time is reminiscent of the standalone injection molding cycle times covered in Chapter 8, but there are some differences, so be careful not to just reuse the equations learned from that chapter. In some sense, the process is somewhat simplified because all the injections will be at relatively low pressures with easy flowing waxes, meaning that the waxes can be injected at their maximum flow rate throughout the process. For the wax mold manufacturing time, again, it's similar to standalone injection molding. It accounts for the mold shape generation based on the geometry of the part, looking at the internal and external patches. It looks at the material removal of the mold, the time it takes to make and fit the ejector pins, and finally, the additional time factors based on the tolerance and surface finish effects. The next column is the cycle time to assemble the ceramic tree cluster. And for this, you need to calculate the time to assemble a single pattern. Even though most of the wax pattern is generated via injection molding, operators still need to attach separate wax pieces and additional features for things such as cast paths. Then you need to calculate the time to assemble multiple patterns into one cluster, which will be highly dependent on the size of each individual pattern and the packing density of the cluster. Then, these last three steps estimate the time to coat the cluster with your slurry, which depends on the number of coats required. And then the final stage that we'll account for here on the right is for post processing time. And this stage accounts for the post processing steps that are required of all investment castings in order to retrieve the final pattern from the cluster. In other words, this doesn't account for the additional machining processes or the surface finishing. This stage has you calculate the time to break away the fired shell from the solidified tree, the time to clean the part, and the time to cut each individual pattern off of the cluster. And that pretty much covers the main components that go into the total production cycle time as provided in this reference. One flaw with this estimation model is that it doesn't include the time required to fire the individual ceramic clusters, pouring the molten metal, and cooling times. But for the sake of estimating, it's pretty comprehensive. On this version of the tree, I've just included the corresponding equation numbers and the page locations to find these equations on your own, to learn more about the context of where these equations are used and some of the variables that are required to use them. And finally, where applicable, I've included the equations themselves for quick reference, or stated if this is typically a given value. So that's all the information I wanted to share in this video. To summarize each of the sections we covered, we first talked about the details of the investment casting steps and how they alleviate many of the constraints on the physical part properties in exchange for the long lead times and tooling costs. We looked at the high level pros and cons for this method compared to comparable casting methods. We then expanded on these similarities and differences by looking at how the design guidelines for this method translates and deviates from guidelines we are already familiar with. And then finally, we laid a foundation for navigating how to estimate the process and cycle times required for investment casting. There are two key takeaways from this video that I'd hope would stick with you when assessing options for manufacturing methods. Then the first would be that investment casting is a great manufacturing method for small to medium production of complex components. The second key takeaway would be that the design guidelines are relatively easy to remember if you have prior practice or knowledge with other casting or molding processes, and that investment casting will almost always be the most forgiving option for many DFM requirements. This was a really fun video to research for and make, so I hope you were able to learn something valuable from it, and thanks for watching.